has informed you that the title of the lecture today is about the processing and refining of laterite nickel ore by pyrometallurgy. We are focusing only on the RKEF, retroactive electric furnace technology. And actually, I know a little bit about the process. I'm not expert, Pak Imam. There's a lot of expert outside. So if you got this material, so please do not upload this material to the internet. Before we start with the production of the nickel, I will show you in this slide the nickel production and uses. If we see the data from 2018, around 2.2 million ton of nickel was produced, and this nickel come from nickel sulfide ore and laterite ore. Yeah, around 700,000 ton of nickel, or 0.7 million ton of nickel coming from the sulfide ore, and more than 1 million, in this case it's 1.5 million ton of nickel was produced from laterite ore. Yeah, most of them in the last 2 years coming from Indonesia. And this laterite ore can be divided into two types, limonite and saprolite. And saprolite ore will be processed via pyrometallurgy to produce NPI or to produce veronickel. And the nickel from limonite will be extracted via hydrometallurgy to produce nickel sulfate or the other nickel products, what we call is class 1 nickel. So the nickel product can be divided into two classes. The first is class 1 nickel and the other is class 2 nickel. Why we call this class 1? Because we can use all the product from this class 1 nickel to produce everything contain nickel. For example, here to produce nickel alloy, to produce special steels for electroplating, including also for stainless steel. So nickel class 1 is actually, we call it number 1 nickel, nickel class 1. We can use this nickel for all purposes. And for nickel class 2 nickel, the utilization, this is only for limited to the stainless steel. So we can use nickel class 2 only for stainless steel. It is not possible to use, for example, for nickel alloy. If you want to use the nickel class 2 for nickel alloy, we should remove iron. We should convert, for example, to the nickel mass, and then we remove iron to get the pure nickel, and after that we can use it for the nickel alloy. Most of nickel, if you see from this diagram, most of nickel is used for stainless steel, around 1.6 million ton of nickel. That was in 2018. It used for stainless steel, and the rest is used for the other purposes. For example, here for nickel alloy, for special steel, for electroplating, for battery, etc. If you look on the data from 2020, the nickel produces around 2.4 million tons. This is the proportion of stainless steel, 73%, and for nickel base alloy around 9%, and for batteries around 8%. But we know that in the future there is more nickel, or more nickel will be used for battery, for EV, for electric vehicle. So in that case, if we see the prediction that in 2030, is around 4.5 million tons of nickel will be produced worldwide. And the proportion of nickel for battery increased from 8% to 27%. The majority of the nickel, if you see from this data, is still stainless steel. Yeah, so this is number one, is the utilization of nickel, and number two is for battery. And the third is usually for nickel-based alloy, which is used for the other purposes, for example, for turbine, for jet turbine, etc. In the diagram on the right hand below, it shows the production of nickel that was collected from 2000 until to 2021 or 2020. We see the green color is the nickel production worldwide, and the red one is the nickel price. At the moment, nickel price is around 25 to 30,000 ton US dollar per ton. Currently, it's around 25,000 to 30,000 US dollar per ton is the current price of nickel. In the last 3 months, the nickel price has achieved around 50,000 or even more, but this is not what to call stable for a long time. It's just for a short time due to the war in Ukraine and Russia. If you see the stainless steel production, because most of nickel is used for stainless steel in 2020, around 1.75 million ton of nickel is used for stainless steel. We see the production of stainless steel worldwide. In the other country, for example, in US, in Brazil, European Union, including South Africa and other Asia, including also Russia, the nickel production is more or less not much changed. It's stable. For example, here in US is around, how much is it? 2 to 3 million ton per year is in US. But huge increase of production you can see in China. Here is with the colors, the orange color. So you can see the production of stainless steel in China in 2001 around 700,000 ton in that year, and now the production increase now is more than 30 million ton in 2020. And also Indonesia start to produce stainless steel in 2017. It's around 4.7. Now is actually more than 3 million ton, or close to 5, yeah, close to 5 million ton is the current capacity and also production in Indonesia. And most of the investment coming from China. Now also most of the investment for nickel plant in Indonesia coming from China, and yeah, they process directly the product from the RKEF plant. The product is nickel pig iron. They process directly into the stainless steel. If you look about the stainless steel, because it's the first use of the nickel, or the common use of nickel is for stainless steel. You see there are around 3 or 4 grades of stainless steel, which is shown here. The first one is 200 series. 200 series. It actually belong to austenite stainless steel. In this case, for example, for the grade 201, we see the content of nickel is around between 3.5 to 5.5, and the chromium is 16 to 18%, and nitrogen less than 0.25. And in this case, most of nickel is substituted by manganese. Yeah, we increase the manganese content because the manganese and also the nickel is what you call a stabilizer for austenite phase. So if we add more manganese, the steel, the phase in the steel will be austenite. So for 200 series, yeah, most of nickel is substituted by the manganese. The common or the most what to call the largest portion of stainless steel produced worldwide is austenite. This 300 series. The most common is 304 stainless steel. If you see for this grade, the nickel content is around 8 to 10.5%, and chromium is 18 to 20%. And 316 is also more or less similar to 304. The difference is the molybdenum content is added. The molybdenum is added to the 316, and also the nickel content increased to 10%. They are minimum. But the other, these two steel grade, these are 400 series. What we call is ferrite stainless steel. In this stainless steel, usually there's no nickel. The nickel is close to 0%, so we do not add any nickel there. In some grade, the nickel content less than 4 or less than 5%. And the last one is for duplex stainless steel. If you see the production of this kind of stainless steel, the 200 series is given here with the green color. It's for 200 series. The content of nickel is less than 6% or less than 8% in general, and most of nickel is substituted by manganese. And then the most popular stainless steel in the world is 300 series. This is including 304. It's the most common. I think this steel grade is produced more than 30% worldwide. 304. And the last one here, we see the 400 series. It's 400. And the small portion here is only the other steel grade, including duplex, including precipitation hardening, and other kind of stainless steel. This is utilization from stainless steel. Yeah, we have seen from this picture. I back again to the first one. So we see that the nickel, the end utilization of nickel is actually in this time is actually for stainless steel, and the others for sure for the other steel grade. If we're talking about the pyrometallurgical road, we produce usually ferronickel or NPI, and this kind of what to call semi-finished products is used as raw material for stainless steel production. Maybe you have gotten the course about the sulfide nickel ore, how to process the sulfide nickel ore. On the left side, this is the typical mineral for the sulfide nickel ore, pentandite or laterite. And today we talk about the laterite nickel ore. Usually, if we look inside of this ore, it contains nickel around 1 to 3%, cobalt a little bit less than 0.25% is maximum cobalt content, and iron is depend on the layer, depend on the type of laterite nickel ore. Content, for example, for limonite, it could be between 30 to 40%, and for saprolite type of laterite nickel ores, the content of iron between 10 to 25, something like that. And there's also crystal water around 10% to 15% is maximum. In this ore, it contains always water, always moisture, water inside. The moisture content is between 30 to 40%. And for this ore, is until today, the people has tried to make concentration, but it was not successful. Now we can say that for this type of nickel ore, it's difficult to make a concentration, to make upgrading, to increase the nickel content, for example, from 1 to 3% on the earth, on the surface. We increase it to, for example, 10%. It's very difficult. It's not possible at the moment because if you see the nickel not free, the mineral content nickel is not free. It's always in the other minerals. It is different if we compare with sulfide nickel ore. We can make concentration on the earth. We can see that the content of nickel is around 1 to 3%. Due to concentration, we can increase the content of nickel to 6 until 6 to 20%. This is the typical route to process both type of nickel ore. For nickel sulfide, usually it processed via pyrometallurgy, smelting, refining, and process concentrating to increase the nickel content. And then we get the final products, nickel, copper, because copper is always there, always in these raw materials. And we get also some PGM like gold, silver. And for laterite nickel ore, it was told you before that it was classified into two types, limonite and saprolite. For saprolite nickel ore, we should use pyrometallurgy. For sure that saprolite nickel ore can be also processed via hydrometallurgy. For example, if the nitric acid is used instead of sulfuric acid. Yeah. For example, the direct nickel technology is they can process both kind of nickel ore, saprolite, and also limonite. For limonite nickel ore, the common technology is actually leaching, acid leaching, for example, which can divide it into two types: atmospheric leaching and also high pressure acid leach. And the products from the limonite, we can recover nickel in the form of mixed hydroxide precipitate, or after that we can refine it further to the nickel sulfate or even to the metallic nickel. Similar also with the cobalt. The product is actually what we call nickel class 1 nickel. We produce this class 1 nickel. For sure that the class 1 nickel is more expensive compared to class 2 nickel. Yeah. And via pyrometallurgy, we use drying to remove surface water, moisture. Its content roughly 30 to 40%. And then we charge the dry ore into the rotary kiln for calcination, to calcine calcinize the nickel ore to remove the crystal water. And then we add also in this rotary kiln reductant to reduce some amount of nickel oxide and also iron oxide. And then we smelt all the calcine from the rotary kiln to the electric furnace. The product is for sure pure nickel or nickel pig iron, or we can also add sulfur in rotary kiln. We can add sulfur in rotary kiln to convert nickel oxide into nickel sulfide, and then we smelt into the electric furnace, and then we can remove iron by using, for example, Pearl-Smith converter to remove iron by adding flux, silica in this case. And the product is what we call nickel matte. And this nickel matte the end product is similar to the hydrometallurgy. We can produce pure nickel, and we can also produce nickel sulfate for the other application, what we call is class 1 nickel. If we do not add any sulfur, so the product is actually class 2 nickel. The product is ferronickel or nickel pig iron. What is different between ferronickel and nickel pig iron? We talk about ferronickel. This is the common definition. Ferronickel, the nickel content is more than 15% is common definition. And for nickel pig iron, the nickel content is less than 15%. But on the other thing, we should also consider the sulfur content. Sulfur content. Usually, if the product is ferronickel, for sure there are crude ferronickel or refined ferronickel, but usually the ferronickel is refined to remove the sulfur from around 0.3 to even 0.8% or even 1% sulfur is removed. There are refining facilities to remove the sulfur content. To the we get in the final product, the sulfur content is less than 0.03%. This is the common product of ferronickel. If you see the ferronickel plant worldwide, there is always the nickel refining there, always the desulfurization facilities there in order to remove sulfur. For nickel pig iron, the nickel content is less than 15%. The common content is around 10 to 12%. In that case, the sulfur content is around 0.2 to 0.5%, and they sell the product with the high sulfur content. This is what we call nickel pig iron. Nickel pig iron is not refined, and also the nickel content also less compared to the ferronickel. This is the main difference. Actually, some people call this one is high-grade ferronickel, and for NPI they call low-grade ferronickel. It's also correct. This term is also correct because for NPI the content of nickel less than 15%. Maybe you have gotten from the lecture before about the processing of sulfide nickel ore. If you see from this diagram, this flow chart, the first is the nickel content in the ore around 1.5 to 3%. This content is increased to around 15%. Nickel in this case in the form of concentrate. And we get also copper concentrate, which is sent to the copper smelting. And then this nickel concentrate will be smelt. For example, they use this flash smelting technology in order to remove the sulfur in the nickel concentrate. And then the product is nickel matte, mixing between nickel and also copper is there, and also iron. This is the product from the precipitate converter, and this is not the end. There's a long way, in order to get the final products, nickel metal or refined nickel. It's very long route in order to get the final product. You can also recover the copper metal. So now we're back to the laterite nickel ore. If you see from the top, the concentration of the nickel, iron, silica, magnesia, alumina, chromite, magnesia. You see here the top soil. Also we call iron cap. The iron content is in the form of Fe2O3. We see here the red line. The iron content, it could be close to 50%. more than 40%, yeah, in the iron cap. And then below the topsoil or below the iron cap, we see here the limonite layer. The content of the iron is more than 25%, and it contains also huge amount of alumina. We see here the yellow line here for alumina, and also they also contain the chromite. Chromite, you can see here the chromite content around between 3 to 5%, and alumina is between 3 to 6 or 7%. Limonite layer contain less nickel. Nickel content is around 1.5, 1.3, maximum is 1.5, 1.4 is the common, or 1.2 is the common content of nickel in the limonite layer. And the less magnesia also less than 5%. In some cases, it could be around 6%, and also less silica content, the brown color, this one here. Less magnesia, less silica. We don't pay many attention to this kind of ore, because this kind of ore will be processed via hydrometallurgy. It's a common technique today. It uses HPAL, for example, to process the limonite ore to get the product of MHP, and then it can be converted into the nickel sulfate. And the other processes could be atmospheric leaching, heap leach, Caron, DNI, and also STAL, which is currently developed in Indonesia. And for saprolite layer, you see here, this is the color of the saprolite. The color is like what to call brown color. This is a dark brown. This is light brown color. Sometimes you can see also the green color there in saprolite. So the content of nickel at the moment is more than 2%. It's difficult to find at the moment. The common content of nickel in the saprolite ore Indonesia is around 1.6 to 1.9. Maximum is in some area we can still find the nickel content around 2.2% in some area, but and the common range is around 1.6 to 1.9, which is used as a raw material for ferronickel or NPI production. And the iron content is less than 30%, in the range of 10 to 30%, and it has high content of magnesia and also high content of silica. The cobalt content also less compared to the limonite layer, and also the scandium content also less compared to the limonite layer. Okay, this is the type of nickel ore. This saprolite nickel ore. From this saprolite nickel ore, we can recover actually nickel, from saprolite. If we use the LKF technology to produce nickel matte, we can also recover cobalt. If the product is ferronickel or NPI, ferronickel or NPI, so we can recover nickel, we can recover iron, we can recover with both of elements. For sure that in the product we just sell the nickel, nobody valued the iron, Yeah, the nickel content in the product, we say around 10%, and the iron content is around we say 88%, because the rest is some carbon inside, some silicon inside, and less than 2%, or even here is 87 or 86% iron. Also phosphorus as impurities, sulfur as impurities, chromium, small amount of chromium you can find also inside. So we cannot sell. Nobody will buy the iron from ferronickel. They just want to buy the nickel. Yeah? But we extract both together. We extract nickel and iron together. Scandium, most of scandium will go to the slag, and most of chromium also will go to the slag. We have just or the recovery of chromium in the metal less than 5%. And the magnesium, yeah, for sure, we cannot reduce magnesium oxide, and also calcium oxide will go directly into the slag. If you see the valuable metal in the nickel ore, for sure is nickel is number one, or cobalt is actually number one, is expensive one, but the content of cobalt is less compared to nickel. In this case, so we can say that nickel is number one and cobalt is number two. But iron is nobody buy the iron. It is challenging for us to recover scandium in the ore, and also to recover magnesium when it's possible, yeah, to extract the magnesium from the ore. For our as metallurgists, is a challenge for us. What you see here, the valuable metal content in the ore tend to decrease. For example, here the nickel content in the last 20 years or 30 years, the nickel content which is sent to the smelters more than 2%, in the last 20 years. But now the nickel content around 1.8, or even in one plant, they have designed the RKA plant to process the nickel ore with the content of nickel around 1.6%. Is the current situation. For sure that if we have low nickel content, at the end we should put more energy. We give more energy, or the energy requirement will be high in order to process this low grade of nickel. That's what we have now. Ore becomes more complex. It's also big challenges. I will inform you later that for the nickel smelting, we should consider the ratio of silica to magnesia. We should consider this. Usually, the percent of silica and percent of magnesia in the ore should be around 1.8. Maybe now this kind of ore is rare, difficult to find. The silica to magnesia ratio tend to increase. Now, in some location, we have information that the silica to magnesia ratio around 1.5 or around 2.5, or in some locations, so we can have also the silica to magnesia ratio close to 4. It's very challenging for us to process. How to do is a big question. Actually, now, not in future, but now, right now. For metallurgists, the task is if you have low nickel content, your boss, will ask you to produce the metal with the high recovery. They do not care about your problem, but they will require you, they will ask you to produce nickel with high metal recovery, high nickel recovery. Maybe it's also challenging how to keep the recovery is around, even it's possible, around 95%, even when we have the lower grade of the nickel. The plant capacity should be increased. Yeah, this is the task of metallurgy usually in the plant. When you work in one smelting plant, and the operating cost should be low, yeah, in order to get more profit. And the last one, we should also think about the environment. We should also think when it's possible about zero emission and zero waste. We have slag, the slag shall be utilized, and we should not emit it more, or we should not emit it CO2 into the atmosphere. We should find the other way to process the metal without any pollution. This data is actually similar like before. If we're talking about the laterite nickel ore, there are two types, saprolite and limonite. The limonite is now processed via hydrometallurgy. This technology which can be used. The proportion, the current proportion is around 20% or even less, yeah, because most of the RKEF plant is now built in Indonesia, with the capacity is more than around 1 million ton nickel per year. And for saprolite nickel ore is processed via pyrometallurgy. In a couple years ago, the data showed that around 80% of the laterite nickel ore is processed via pyrometallurgy, but I think its current data is more than it. And if you look to the pyrometallurgy technology, there are three types of technology. The first or the largest one of the most common technology used is RKEF. Consists of rotary dryer. We will see it later. Rotary kiln and electric furnace. The product is nickel pig iron or verronickel or nickel matte. The proportion of this technology in the year of 2017 around 93% worldwide. And the second is blast furnace, mill blast furnace around 6%. But I think this technology is now already not implemented or already disappeared. The reason is because of the production cost is very high due to the coke price, coke consumption in the mini blast furnace. Yeah, I think maybe just less than 2% or even less than it, the proportion of nickel which is produced via mini blast furnace. And this is data from 2017. The current data could be, this is close to 97 or even 98%. Yeah. And there is also one technology used to produce what we call is Zulhan ferronickel. This technology is in Japan. It was developed in 1940s. And this technology was originally from Germany, actually, and it was built in Japan in 1940s. So we focus to the RKEF. Another technology is sinter electric furnace. In this kind of technology, they replace the rotary dryer, they replace the rotary kiln with the sinter machine. The nickel ore is sent to the sinter plant. It's mixed with calcium oxide, mixed with coke as fuel, to produce sinter, and then sent to the electric furnace for smelting. We mix with coke or semi-coke as a reductant or anthracite, and then we send to the electric furnace. If you have any question, please ask directly. This what to call diagram shows the complete processing of nickel ore, saprolite nickel ore, and also limonite nickel ore from the ore until the final products. Yeah, for example, here, if you look to limonite nickel ore, it will process via hydrometallurgy, HPAL, atmospheric leaching, heat leach, etc. is the current process. And the semi-finished product is MHP or MSP. And this semi-finished product will be refined further to produce nickel sulfate or cobalt sulfate, or we call it nickel class 1, and used for battery or for chemicals. And for saprolite nickel ore, the current technology or common technology is RKEF. We can produce it into the nickel matte. Yeah, we can process the saprolite nickel ore into nickel matte. The content of nickel is around 78%. And this nickel matte can be processed further to produce nickel sulfate or to produce nickel oxide sinter or to produce nickel briquette, nickel metal, and we can also recover the cobalt from the nickel matte. The other product is ferronickel and MPI for sure. For these two kind of semi finished product will be sent to the AOD converter, or we will send to the stainless steel shop, making shop. They will produce slab, stainless steel slab, and then the final product is cold rolled coil or cold rolled coil, with then transfer or sent to the manufacturing industry. Now we focus on the rotary kiln electric furnace technology. If we see the road, there are two kind of road. The left hand road is a nickel ore is sent to the rotary dryer for removal of surface water from around we say here 35% or 30 to 40% of moisture is removed. Yeah, we get in the dry ore here, the product from the dryers is around the moisture content or the water content is around 20%. And then this dry ore is mixed with reductant. Reductant, it could be coal, could be coke or semi-coke. It could be wood chip in the other country, or it could be later on. We can also use wood chip, also biomass. We can also use biomass as reductant for rotary kiln. And the burner or the source of energy for drying coming from the burning of the pulverized coal or the burning of oil or the natural gas. The temperature here is around 300, 400 Celsius degree. And then the content of water in the products here is around 20%. And then the dry ore, or what we call also conditioned ore, is mixed with reductant and then sent to or charge it together with the reductant into the rotary kiln. We can mix it in the rotary kiln. Similar with above here, with rotary dryer, we can use pulverized coal, we can use oil or gas as source of energy. Yeah, or for burner in the rotary kiln, the temperature maximum is around 1000 Celsius degree is the gas temperature. In some cases, it could be around 1100 or 1200. And we got here the products. We get here the product. The product is actually the calcine at a temperature roughly between 600 to 800. And then we transfer this calcine to the electric furnace, and we charge into the electric furnace at a temperature maybe less than 600, yeah, because there's some heat loss during transportation and also When we put it into the bin, there's some heat loss. It could be the temperature is around 500 until 600. There's temperature of calcine, which is charged into the electric furnace. We use electrode paste to form the electrode to get electrode. We form the electrode from electrode paste from graphite, and then the product we get NPI, or we get a crude ferronickel, which is then refined further into the ferronickel. Usually here we use desulfurization. In some plant they use also decarburization, and also for sure if we use we do the carburization, we can also remove the silicon, the siliconize, and the siliconization also can be conducted as well. And in this case, if we do only desulfurization, the product is called a high carbon ferronickel. And then if we remove the carbon by oxygen drawing in converter, so we can also produce low carbon ferronickel. The phosphor content should be controlled, and the phosphor content in the crude ferronickel or in the NPI should be controlled from the raw material, from the nickel ore. If we do the decarbonization, and also we do the for sure, we remove also silicon. In that case, we can also remove phosphor. In this case, we can remove phosphor. But if we produce only high carbon ferronickel, we should control the phosphor content in the ore, because the requirement in the product phosphor content is usually should be less than 0.04 or 0.03% is normal phosphor content in the product. If we have the phosphor content, for example, more than 0.05%, I think in this case the buyer will give you penalty, because phosphor is difficult to remove for stainless steel making. If you want to produce stainless steel, if they have charged the chromium, the ferrochromium, they have charged the ferrochromium into the AOD converter. It's very difficult, or we can say it's maybe not possible. We just remove small amount of phosphor. We can say it's very difficult to remove phosphor. So for the phosphorus content is very, very strict. In this case, sulfur, it doesn't matter actually. We can also charge directly the ferronickel NPI from electric furnace into the AOD converter, and we can remove sulfur at the end of the AOD process. At the end of AOD process to produce stainless steel, we add lime, CaO, for sure. The first we add silicon, or we add aluminum to reduce the chromium oxide, and then together with ferrosilicon, we add CaO. We add also dololime. We add dololime, CaO, and most of cases we add fluoride, fluorspar, CaF2, and this slag can be used for desulfurization. It doesn't matter. We have observed that from some stainless steel making plant, the sulfur content around, we say that 0.1%, it can be removed to less than 0.01%, 0.01% sulfur at the end of AOD converter. So phosphor is really very strict about the phosphor if we produce the NPI or we produce high carbon ferronickel. If we produce low carbon ferronickel, the phosphor can be reduced during the oxygen blowing and converter, for example. Yeah, there are two what we call two roads. The left hand side, and the other is on the right side. On the right side, what is different? The main difference is the utilization of the off gas is the main difference. In this case, the off gas from electric furnace is sent source of energy for rotary dryer, and also similar with the off gas from rotational. In this case, yeah, in some plant, this is not required. Oh, sorry, it's still Indonesia. Sorry, it's similar like this. Yeah, fuel, purified coal, oil, gas. So in some cases, we do not need any fuel. The energy can be supplied 100% from the off gas from electric furnace and also from the off gas of rotary kiln. This is a more the new installed LKF plant use this kind of route. They can better utilize the energy and from the off gas in order to reduce the overall energy consumption on the other sources. This is we see again from the first route three kind of equipment we need. The first is rotary dryer, and the second is rotary kiln, and third one is last one is electric furnace. In this case, we just produce ferronickel, crude ferronickel, and MPI. And some cases, if you want to refine this product, so we should add one equipment. Usually, we use it one ladle. We tap all the metal into the ladle, and we can refine it to remove. We can refine the crude ferronickel or MPI to remove sulfur, desulfurization. We can conduct it, and then after that, we can use oxygen. In some plant they use converter. The other plant they use a ladle to remove the rest of carbon and silicon, and also they can also remove phosphor in order to produce low carbon ferronickel. So we look one by one. Nickel ore will be charged to the rotary dryer, and fuel will be burned here. Yeah, in this case, we do not utilize any off gas from here, or we utilize. This is the one line here to utilize. This is one option. We can also utilize this off gas from electric furnace, and we can send it here, or from rotary kiln. We can also send directly. Actually, from here we can send directly to the rotary dryer. In that case, if we use the hot gas from electric furnace from rotary kiln, so we can reduce the consumption of fuel. Now we have here a huge amount of gas. The temperature minimum is around 400 to 800 is a range temperature, and we charge the nickel ore co-current in the same direction with the hot gas. Here we use hot gas. With the temperatures is 400 or 300 is minimum. 400 is common, is 400 to 800 Celsius degree. And then this hot gas, huge amount of hot gas contact directly with the nickel ore, with the wet nickel ore. And during the movement of the ore and its contact with the hot gas, the moisture is released, the moisture is removed. Yeah. And so at the end, we have here the moisture, H2O will go to the off gas together with dust, and the product, what we call conditioned ore or dry ore, is content of water is around 20%, and this is sent to the rotary kiln, and then it charged into the rotary kiln together with reductant. In some cases, we need also flux. For example, here to adjust again the silica to magnesia ratio. In the final slide, silica to magnesia ratio. Flux is added. Could be dolomite or limestone is added to adjust. Also, in some cases, if you do not have any copper cooling in the furnace, in order to increase the lifetime of the refractory material, so we add also flux like limestone. In that case, we can increase the lifetime of the refractory to roughly 5 to 6 years. If we use the copper cooling, we do not need any flux except if we have the SiO2 to MgO ratio more than 2.2. In that case, we must add flux. But if you use copper cooling without any flux addition, add the SiO2 divided by MgO roughly around 1.8. We use copper cooling. In that case, the surface life of refractory more than 10 years. In some plant, we have got the data more than 20 years. And in this rotriculum, yeah, we can see it later. Yeah, the process in rotriculum it divided into 3 zones. Actually, the first zone is actually for the removal of surface water. The second zone is roughly to remove the crystal water, and the last zone is for pre-reduction, and also to increase temperature. Maybe also some of crystal water also will be removed in this area here. And the product is calcine, and this calcine will be put into one container, will be filled into one container. This container is lined with refractory, and then this container will be transferred to the silo or to the bin of electric furnace by crane, and then later on this material flows by gravity, yeah, into the furnace. The temperature in the furnace is around 1600 degrees, and then you can get slag, you can get vermicle and PI. In this case, if you do not use the off gas from the rotriculum and also from electric furnace, we need, you see here, we need 3 stack. Is one stack for rotary dryer, second stack for rotriculum, and the third stack for electric furnace. We need also for sure ID fan, yeah, ID fan, 3 ID fan, and we need also 3 dedusting system, backhose or electrostatic precipitator. Yeah, we need these 3 kind of dedusting system. And in this equipment, for sure that we need energy. For fan, for example, yeah, we need energy, we need power, electricity, yeah, to operate the ID fan. So we need the other equipment. In this case, actually, we have relatively high electrical energy consumption, and also high fuel consumption. We need more fuel for rotary drive. Yeah, this is the limitation of this kind of technology. Is actually the old technology. Now the current technology, there is a trend to utilize the heat from the off gas from the furnace and also from the rotriculum, and they can transfer it directly to the rotary dryer, the source of energy. Also similar is here. In this case, we need only 1 stack at the end here. Theoretically, we need only 1 stack, but it is very often they also have 1 stack here. First, what to call spare. Yeah? If there is some trouble here, so they can do the bypass. They can send off gas to this stack. If everything is normal, so we use only 1 stack after rotary dryer and 1 dedusting system and 1 ID fan. Yeah, maybe it is a little bit complicated to operate this plant because it could be if the temperature or the off gas amount is not enough. Maybe we got the nickel ore, the content of water is still high. Maybe, yeah, in that case. But it's a good idea to utilize the energy from the off gas of electric furnace and also from rotriculum as a source of energy for drying. Now we look one by one. We have also discussed before. Rotary dryer. The function of rotary dryer is actually to remove the water content or moisture around 35% to 20 to 23%. With the aim is to facilitate the feeding process into roticulum is the aim. If you see this, the common, laterite nickel ore, if there's rain, so the water content, it could be in this case more than 40%. And the nickel ore, if you see in this case, will adhere or will stick on the conveyor. If we transfer this wet nickel ore directly without drying into the roticulum, so we can save energy for sure. But this nickel ore will adhere or will stick on the surface of the silo or on the surface of the bin. We cannot charge it, the ore from the bin into the conveyor. It's very difficult because it sticks directly into the surface of, it's very difficult. In that case, before we send to the roticulum, so we must remove the water, and this water shall be controlled around 20 to 23%. We must control the ore is maximum is around 20% is the common value for the moisture content in the dry ore from rotary dryer. The aim is actually in order to get the stable operation of the roticulum and also the stable operation of the electric furnace. If we have the water content, for example, today is 25%, tomorrow 20%, we should add reductant also based on this value. We must add, for example, for 20%, for example, we add reductant around 4%, and for 25% water in the dry ore, so we should reduce it, maybe 3.8%. You know why? Because during the drying, the first period here in roticulum, so the water is evaporated. So we have here the true dry ore. If we add similar 4% reductant, we do not care for 25% or for 20% or for 15%. We add a similar amount of reductant. For sure, at the end, we have more carbon. In this case, we have more carbon. In this case, we have less carbon. It will impact on the product, from electric furnace. If we add more carbon, it means the carbon reduce also iron oxide. So we have lower nickel content in the product. If we add less carbon, less reductant, less carbon, so we get nickel content is high. But in this case also nickel recovery low. In this case, nickel recovery high. And if you want to sell the products to the buyer, it's very difficult to sell the product because today you produce the nickel content 15%, tomorrow you produce 25%. The product is not stable, and because of that, we should control this by drying. We should control the product. In order to get the stable product, we should make sure that the drying process occur very well. Yeah. You can what to call we should control the dryer. We should control the dryer. We should control also the moisture content in the dry ore. Yes, because the aim is actually to reduce the moisture content in the ore, yeah, in order to facilitate or to get easy to feed to proteculum and also to get stable products. And also the moisture content in the ore should be kept around 20% in order to minimize the dust formation. For sure that if we reduce the moisture to 0%, maybe the dust formation is more than 50%, maybe, or more than 30% is, or more than 10% or more than 20%. The dust formation will be high. If we keep the moisture content around 20%, the dust formation from the rotary dryer is around 2%. Is the common value is around 1 to 2% is the common value. The next is actually rotaculum. The task of rotaculum, the first is to remove residual moisture from the ore. Yeah, at the input we get 20%, and this ore should be removed to 0%. And the removal of moisture takes place around 1/3 of the rotaculum in this area. And then remove crystal water to prevent explosion in electric furnace. Usually the crystal water should be less than 1%. And the crystal water, we can see the reaction here. The crystal water, it could be in the form of goethite. If you have goethite at roughly around 500 Celsius degree, 500 to 600 Celsius degree, we can dissociate the goethite into hematite and water. Yeah, the dissociation of goethite. We can remove the crystal water in the goethite, so we get hematite. This is in the case of limonite ore usually. For saprolite ore, the minerals is garnierite, or it could be antiquarite or serpentine. Yeah, there's also crystal water in the mineral at temperature roughly around 600 to 700 degrees. We can dissociate. We can remove the crystal water. You can see here. We can make it free from the crystal water. We can also dissociate the nickel in this mineral into the nickel oxide and Mg into MgO and SiO2. And then the last part is around here at the center of the reticulum, or in this area here. And the last part of the reticulum, we can also reduce the nickel oxide into nickel metal. We say the common value is around 20 to 25% of nickel oxide is reduced to nickel metal, and the rest is still in nickel oxide. Around 75 to 80% is still in nickel oxide, and almost all hematite. After we dissociate this kind of mineral, hematite is reduced to iron oxide, to wustite. It's around 100%. We can reduce the oxygen here to produce 100%, close to 100% wustite. And then for sure that from hematite we'll go first to magnetite, and then the last is to the wustite. Around 5% of wustite is reduced to metallic iron. 95% is still in the form of 95% in the form of oxide, in the form of wustite, and around 5% or even less than 5%. It depends on the condition in the reticulum in the form of metallic iron. And last one here, we discharge the calcine. We produce the calcine at temperature. Yeah, there's a lot of data here. Some people say 600 to 800, 750 to 900, depending on the plant. Maybe this value 750 to 900 Celsius degree. The aim is to get to keep this temperature is actually to reduce the electrical energy consumption in electric furnace. If we charge hot calcine into the furnace, for sure that we can reduce the overall energy consumption for smelting. Okay, then we go to the electric furnace. Yeah, after the calcine is transferred to the silo or to the bin of the electric furnace, the calcine flows into the electric furnace. In electric furnace, the nickel oxide is further reduced to nickel metal by CO gas. The CO gas will be formed at the bottom, at the center here. Is a CO gas will be formed at the center here of the electric furnace, and this gas, during the moving up of this gas, the nickel oxide in the calcine can be reduced to nickel metal. If you see the main composition of the off gas is still CO. CO is around 70%. Around CO2 is around 30%. It's roughly, yeah, roughly like this. And just a small amount of CO gas is used or utilized to reduce nickel oxide and also to reduce the iron oxide, because it's short distance. Also short distance. The contact is also very short, also very short, and the contact time of CO with this calcine. And then iron oxide also can be reduced also with the CO gas into the iron, and the product is CO2. The main reactions actually occurs during the heating up of the calcine, and also some reaction occur here in this area. Yeah, in that area, nickel oxide is reduced by carbon. Also in the calcine, also the reaction also take place. Some of this reaction, and iron oxide is reduced by carbon to produce nickel and iron. This silicon oxide will reduce by carbon, mainly around the electrode, mainly around this area where the temperature is high and the carbon is there, and this is also the cause of the consumption of graphite electrode. So this graphite electrode will consume due to the reaction with the slag, with the SiO2 in the slag. So we get silicon metal. This silicon metal will dissolve into the final products, and phosphorus also can be reduced by carbon. Actually, we do not want this reaction to take place in the furnace, but as we heat the calcine and we add the carbon, for sure, if you reduce the iron oxide to the iron, and this reaction also take place, and we get these impurities into the products, and chromium also will be reduced by carbon. We get also chromium in the products. It's around in this area, in this slag area. So the chromium oxide and also silicon oxide is reduced to its metal. And last year we got the product is ferronickel. This contain carbon, silicon, chromium, and phosphor, and sulfur. The sulfur, most of sulfur coming from the reductant. If we see the coal usually contains sulfur roughly less than 2%, but the requirement of coal for sulfur for reductant sulfur content should be less than 1%. And sometime in one plant, they are very strict. The sulfur content should be less than 0.5%. Yeah, in order to get lower sulfur content in the product. We do not have, or we have small amount of CaO in the slag, so the desulfurization in the furnace, we can say less than 5%. We cannot, principally, it's difficult to remove sulfur or to conduct the desulfurization during the process in the electric furnace, except if we add here flux, if we add limestone, so we can remove sulfur from the metal. This data show you the typical electrical energy consumption. It depends on the temperature of the calcine, which is we charge it into the furnace. If we charge at room temperature, we see here is a typical calculation for sure. The energy consumption is very, very high. Yeah, the common energy consumption right now for the furnace is around 500 to 550 kilowatt hour per ton of calcine. Is a common per ton of calcine is common energy consumption, electrical energy consumption. And in this case, the theoretical calculation without any losses to the environment. So we see, and in this case, 500 to 550, the temperature of calcine is around 600 in this line here. In this line, the theoretical calculation is depend on the grade of the steel that will, the grade of raw nickel that will be produced. If we produce lower nickel content, it means that most of iron oxide shall be reduced by carbon. We produce more iron to dilute the nickel content plus CO. And this reaction is endothermic reaction. Enthalpy is positive. So if we have more iron metal into the product, so in that case, the energy requirement is high. It's a theoretical calculation. If we produce, for example, here 20% nickel, so the energy requirement is here. If we produce MPI, the energy requirement increase a little bit, yeah, around 50 to 100 kilowatt hour per ton of calcine. This diagram shows if we have the calcine at room temperature, 25 degrees, so the energy requirement for electric furnace is very high. So because of that, we try to charge the calcine into the electric furnace at a higher temperature. We put it into the tank, to the container, and then we send it directly to the bin, and then we should cover. We should have a cover here. We close the surface of the silo or the bin in order to reduce the energy or the heat losses to the environment via, for example, radiation. We can do it, and this is also the common practice in industry. They put the cover on the bin, on the top of the bin. So, is there any question? Next, we continue to the silica to magnesia ratio in the slag. We see from this data, this diagram was published in 1988 by Diaz. And this is the new data we found in the literature in 2004. It was published by Foreman. We see that there is a relationship between liquid temperature of the slag or melting point of the slag with the silica to magnesia ratio and to the iron oxide in the slag. Here is the plant in the world. They operate the plant with the silica to magnesia ratio. If we see from this curve or from this diagram, similar also from the diagram above here, it's similar. This old data is new data. If we see from this diagram, the silica to magnesia ratio, the most of the plant in the world operate the plant with silica to magnesia ratio between 1.8, 1.6, yeah. If you see here between 1.4, 1.1, 1.2, 4, 6, 8, between 1.6 to 2.0. That's the range of silica to magnesia ratio between 1.6 to 2.0 is the range. Most of the plant operated with 1.7, yeah. And in this diagram shows you also there are one plant operate with silica to magnesia ratio close to 3. This plant is actually in Cerro Matoso in Colombia. But according to the new data, we have got new data that only for commissioning, they operate the plant at this high silica to magnesia ratio. After that, they move it to this area as well. What is the consideration about this silica to magnesia ratio? Actually, the experience was collected by INCO in 1970s, 1980s. At that time, they have 2 plants in the world to process the laterite nickel ore. One is in Indonesia, in Sorowako, and the other in Guatemala. The silica to magnesia ratio is very different from both plants. In Indonesia, the silica to magnesia ratio is around 2.5, yeah, and at Guatemala it's around 1.4. It's two extreme silica to magnesia ratio. And at that time, they have observed in this silica to magnesia ratio, slag is relatively fluid. Yeah, slag is fluid, but they have problem with the refractory. After a couple of months, maybe at that time, or a couple of years, 1 year or 2 years, they are the corrosion of the refractory materials. They are the dissolution of refractory into the slag. They have the abrasion of the refractory. And on the other side, at Guatemala, they have observed that the slag is very viscous slag. When they tap, it's very difficult to get the slag out of the furnace. And then they observe also the refractory is what to call there is no corrosion of the refractory material at the Guatemala. Yeah. At that time, from that time, the people try to understand, try to learn the behavior of the slag to the refractory materials, and until now, the plant is operated in this area. And at INCO, at that time, Indonesia, they have 2 kinds of ore. One ore is with high SiO2 to magnesia ratio, and the other ores with low SiO2 to MgO ratio, and they blend these two kind of ore in order to get the silica to magnesia ratio we see here, yeah, in coal, and this is point here in coal. So at the end, they operate the plant with the silica to magnesia ratio is close to 0.0, the 0.0, 2.0, close to here is the silica to magnesia ratio at PT Inco. They mix, yeah. After they learn from this situation. Until now, almost all of the plant operate the furnace with this kind of silica to magnesia ratio. And as I have told you before, that in the future, this kind of ore will be rare. At the moment, also, the ore is already rare. Because of that, if we look now, some plant at limestone, yeah, to increase the to reduce the silica to magnesia ratio or to increase the surface life of the refractory. Some plant also add magnesite, MgO. If they have the silica to magnesia ratio around 3, they add MgO, calculate back how much MgO or magnesite should be added in order to get the silica to magnesia ratio around 1.8. And then also the other plant, if they do not use any copper cooling in the furnace, then also CaO to increase the surface life of refractory material. Two things that should be considered. The first one is silica to magnesia ratio. The other is iron oxide. This iron oxide also very, very aggressive to the refractory materials. The maximum iron oxide content in slag for the current operation of the furnace is around 22%, yeah, between 20 and 25% is maximum in this range. If you see from the data, there's only 2 plants in the world which operating their plant with high iron oxide content. And the other plant, they try to operate the electric furnace with the iron oxide is less than 15%. In some cases, for example, here when they produce NPI, nickel pig iron, they want to take more iron. The iron content in the product should be high. In that case, the iron oxide content could be less than 10%. This figure actually what the people believe until today. They just consider the SiO2 and then CaO, and the last one is iron oxide. Now we think that beside this main component in the ore, yeah, in the slag, so there are also small amount of CaO, a small amount of CaO, but alumina could be high, and chromides in between CaO and alumina. So the presence of this alumina in the slags actually should be considered, and this diagram should be revised. It's actually not only SiO2 and MgO and iron oxide, the presence of alumina in the slag should be also considered. And until today, if we talk about the slag for electric furnace for ferronickel plant, we just consider the iron oxide, then MgO, and then SL2, and then we see at 1,600 Celsius degree, where we show that the whole slag is melted, or we can also get more lower temperature. We can also put here, for example, 1,500 Celsius degree to area where all the slag is melted, yeah, and then they plot their slag composition in this diagram. Yeah, whether the slag is melted or not. Yeah, for example, here we put the silica to magnesia ratio 1 and add the iron oxide content around 10%. Yeah, in that case, it should be the melting point of the slag not 1,500, could be 1,550 in between 1,600 to 1,150 in that case. And then adjust the silica to magnesia ratio in order to get in this area. In this case, if you look the SiO2 to MgO ratio 1.5, this line still not inside of a liquid area, and then 2.3 is too high, and then 1.8 is why. This is the reason why the people adjust the silica to magnesia ratio for the archaic plant is around 1.8 in order to get this point here, this area. Also similar with this graph, and also similar with this diagram here. And then last year, we just observed, we have made a calculation by FeNi. We just observed that the proportion of alumina may influence the liquid temperature. For example, here, if we take this according to the calculation by FeNi for 10% iron oxide slag, not in this line, maybe in that line here for 10%, there's one line here. And we see for sure that this, I don't know why it's a little bit different between the fixed calculation and this diagram. There's not 100% similar. If you see that if we add alumina 1%, we can reduce the melting point, especially when the melting point, when the silica to magnesia ratio is around 2 in this area. So we can reduce melting point a little bit, but at high silica to magnesia ratio, the melting point even decrease more than 100 Celsius degree. It's very high for sure. Maybe this kind of the decreasing of liquid temperature, this is the cause of the slag is very aggressive to the refractory material. Besides, the silica content is high, so the silica content is high, has silica content. It can react with the MgO, is acid, is basic slag, basic oxide, acid oxide. So it can react to MgO. MgO we use it as refractory material. In the other case, by depression of alumina, the melting point also will be decrease the melting point. So the slag later on, we should measure the slag viscosity. This is based on calculation. The liquid temperature from FeNi, and we should measure the viscosity, whether if the alumina present in the slag, the viscosity also decrease. Okay, this is about the slag, about the viscosity, about the melting point, what we should consider for the smelting in the electric furnace. The other cases, or the other one, we should also consider the interaction between iron oxide in the slag with the silicon in the metal. In general, if we want to have a high silicon content in the metal, if we want to have high silicon content in the metal, we should reduce the iron oxide content in the slag. This is a diagram also from Diaz, and Professor Diaz for sure, in 1988. There's a correlation between iron oxide in the slag and the silicon in the metal. If you want to produce ferronickel with high silicon content, so we should reduce the iron oxide. You see here, the maximum iron oxide in that time is around 22%. There is no plant in the world who operated the plant, no plant which is operated at the iron content more than 30%, because it's very, very aggressive to the refractory material. It's very aggressive to the refractory material. So they keep the iron oxide and the content is like less than 25%. So you have low iron oxide, according to this equilibrium, thermodynamic equilibrium. So we have high silicon content. The silicon content sometimes has advantage for the AOD converter. There's no trend to process directly the NPI into the AOD converter, where the molten NPI will be charged directly into the AOD converter. In that case, yeah, we can add a ferrochromium solid into AOD converter. We do not need any EAF for the melting of the ferrochromium or the other kind of material for stainless steel making. We just charge the molten NPI into the AOD and then cold ferrochromium or solid ferrochromium, cold, yeah, solid ferrochromium into the AOD converter, and then for the first time, for sure, we blow in oxygen. We charge the NPI, blowing oxygen, and this silicon into the NPI has we have advantage from this silicon content in the NPI during the oxygen blowing. Oxygen react first with silicon, and this reaction is actually exothermic, so we can produce heat. The temperature of the metal in the AOD converter will be high. In that case, the energy is enough to charge the ferrochromium. So this is the advantage of the silicon content. The current or the common silicon content at the current operation is kept less than between 1 to 2% as a common operation. In this case, if we have high silicon content, for sure, in the AOD converter, we should add more flux, yeah, more flux again. So more energy, more slag will be produced. More slag, it could be also more nickel losses into the slag. The optimum is between 1 to 2%, not to 4%, for example. To 4% is too high, and to remove the energy release is also very high if we have the 4% silicon in the ferronickel. So we can adjust the silicon content. We can adjust by adjusting the iron oxide in the slag, and for sure, we can adjust the iron oxide in the slag by adjusting the reductant, the coal or the carbon or carbonaceous material, which is added into the rotary kiln. Yeah, and also this is the important one in order to adjust the silicon content in the metal. Similar with silicon, carbon also has a similar behavior with silicon. So if you have low iron oxide content, you have high carbon content. And this is some of the operating data from some plant in the world is iron oxide content. This is the iron oxide content to produce. This is for high nickel content. You see here, if you have high iron oxide in the slag, high nickel content in the metal, which means also less iron content in the metal. And in these two cases, we have a little bit less nickel content, around 18-20% nickel, and we have high iron content in the slag. High iron content in the metal, low iron content in the slag. Now for NPI, there's no data here. For NPI, the nickel content is around 10 to 12%. The iron oxide is around similar like this, yeah, around 8 to 7 to 5 to 8% or 10%, less than 10%. But in this case, the difference is if we look what is different between the production of ferronickel and NPI in general. From the raw material, we can adjust the iron to nickel ratio. Is the common what we do. In order to produce ferronickel, the iron to nickel ratio should be around 5 to 7. And for NPI, the iron to nickel ratio is between 9 to 11. Is a common value. In this case, we have the nickel content is around 10 to 12%. In this case, is around nickel content is around 20%. Yeah, we can adjust by mixing, by blending from one ore with the other ore, and sometimes the limonite ore also blended with separate ore. Yeah, that's all about the ferronickel, and this the route to produce nickel matte. To produce nickel matte, we should add sulfur. This is in the case of Pali or Inco at the end of rotaculum, and then this kind of calcine, which is mixed with sulfur, is charged into the electric furnace. There will be melted, and also some of reaction occur in the furnace, and the product is matte, nickel matte. The content of nickel is roughly 28 to 30%, and nickel sulfur is around 10%. And then this semi-product is converted into the final product with content of nickel around 78% and sulfur around 31% by using a prismatic converter. And silica is added. As is similar with copper making, actually, why they add silica in order to adjust the slag, firelight slag, SiO2, FeO slag. This is the reason. Copper, similar with copper refining. And this is the other route in New Caledonia. This belongs to Eramet. They produce both of product. They produce also ferronickel, and they produce matte. The difference with this kind of route, in this road, sulfur is added at the end of rotaculum. In this road, sulfur is added in the prismatic converter. Here is sulfur is added, and then oxygen is blown or air is blown, and then silica is together. Actually, silica and air is blown in order to remove the iron into the slag. This kind of road will be used right now due to the shortage of nickel class 1 for FE battery. If we see the news from SNNC in South Korea, they just purchased the converter from SMS group in Germany. They installed the prismatic converter in order to convert their products, their ferronickel products, into the nickel matte, and then they send it to the nickel sulfate plant. They convert the nickel matte into the nickel sulfate as raw material for battery production. And this kind of route maybe will be installed also in Indonesia right now. And also there are the other alternative technology, which is under development for directly converting the nickel matte from the laterite nickel ore. And it's the other route, sintering electric furnace. They just replace rotary dryer and rotaculum. They replace it with sinter. One limitation of this kind of technology is the sinter ore. The temperature of sinter ore, which is charged into the furnace, is actually less than 200 Celsius degree. Less than 200 Celsius degree compared to the RKEF, where the temperature is around 800. Because of that, the energy requirement for smelting and electric furnace is high. And in this case, the semi-coke is used as reductant, and here also we use fuel for sintering. So the coke consumption is high in this case, and so we need also fuel that is actually similar with rotaculum. We need also fuel for burner here for sinter. As you have been informed before, that the NPI of ferronickel is used as raw material for stainless steel making. Here's a road, one road in Indonesia. So the nickel pig iron in molten state is directly charged into the AOD converter. Maybe in some cases they mix with molten NPI from the blast furnace with the content of nickel less than 8% or around 8%, according to the. It depends on the nickel content in the final products, and they have also ferrochromium in the molten state. But actually, principally, we can also add directly ferrochromium in solid state, and with enough, the energy is enough to convert or to melt the ferrochromium in the AOD converter. And then at the end, after the removing of carbon, we add ferrosilicon and also ferromangan or manganese electrolytic to adjust the silicon content. Ferrosilicon is added also to reduce the chromium oxide from slag, to get the chromium, to get high recovery of chromium, and also to get the final slag, which is used for desulfurization. We should also reduce the chromium oxide, and then we add here also CaO. I informed before that CaO and MgO or dolomite also, CaO and MgO, dolomite also added, and CaF2 is added to adjust the slag composition and can use it. But we see from this kind of combination, become of integration between nickel smelting and stainless steel plant, and also we can use the iron from NPI. We do not need any iron scrap. So this kind of route is actually the most efficient stainless steel plant in the world. Actually, we do not need any energy for melting in the AIF. No AIF required. From the capex also lower, from the OPEX also lower compared to conventional stainless steel making. In the last 2 years, we have made research in laboratory in order to recover the other metal from the slag. We see here is the ore, and we can recover the ferronickel or NPI. There's slag. What kind of valuable metal in the slag? Actually, we can recover. It's a source of magnesium. It was published in the last year, I think. The novel utilization of ferronickel slag, a source of magnesium metal and ferroalloy production. But by carbon, it's actually very difficult to reduce the magnesium oxide. But now we have used metal as a reducing agent for slag, and we show that it can be used as a reductant. We can produce also magnesium metal. The last slide, I think, for the net zero in 2050, that's what we should do. Now, we make also experiment in our laboratory to simulate the rotary kiln and also electric furnace by using pure or hydrogen. We use hydrogen as a reductant, which the aim is to reduce the CO2 emission, to reduce this emission from rotary dryer. Here, for example, if we use fuel, maybe this fuel or the gas, we should not use any fuel here. We can utilize the off gas from rotary kiln and also from electric furnace. In that case, maybe small amount of fuel is required. If the fuel is required, we should see the other source of fuel, for example, with hydrogen. I think hydrogen burner is already developed in Germany for rotary kiln. We can install burner from hydrogen, and actually we can use this as source of energy if the energy from off gas is not enough to dry the ore in the rotary dryer. In this case, we can replace the fuel also by hydrogen, and we use hydrogen here as a reductant. We should not burn all of hydrogen from the burner, and then we should also add more hydrogen to the side lens here to supply the condition for the reduction. But we must pay attention with the explosion because hydrogen is very dangerous when it reacts directly with oxygen. The water will be produced directly. And for the furnace, we should replace the energy, the electrical energy. Now is coal or oil is used. guess we can use biomass, for example, or we should use the other kinds of electrical energy, for example, from solar energy, from wind energy, and from the other energy. And we now simulate this process in our laboratory, and then we try to see whether the nickel oxide or iron oxide can be reduced 100% in reticulum, and then we smell it in electric furnace, whether we can recover, we say, more than 90% nickel. And we make this experiment laboratory. And it's the other thing we should think about the future alternative method to reduce the CO2 emission. The current, if we use the power plant from the coal, the CO2 emission is around 70 ton per ton of nickel. Yeah, so CO2 is around 70 ton per ton nickel. It's very high due to mono. We should find the other way. Okay, that's all. Thank you very much for the attention. If there's any question.
Thank you, Pak Zul. Usually it is time now for question and answer, and we got already question in the chat, but we will prioritize first question from the Zoom. Okay, somebody already raised here the hand. Nabil, you can ask the question to Pak Zul, please.
Thank you for the opportunity, Mr. Liman. I want to ask question nickel processing. So from nickel processing and refining route, I can see that to produce pure nickel, we use limonite ore. So my question is, why do we use lower grade content of nickel to actually produce pure nickel or class 1 nickel, not using saprolite that actually has more content of nickel? Thank you, Pak Zul.
Actually, your sound is a little bit vibrating and not clear, Nabil.
So the question is, can we use limonite ore for KF, or what is your question?
Okay, from the text, Nabil asking, from nickel processing and refining route, I can see that to produce pure nickel, we use limonite ore. Why do we use low grade content of nickel to produce pure nickel class 1 nickel? I mean, why we use hydrometallurgy for low grade ore? I think that's the question, to produce class 1. Why we don't use saprolite? Why don't we use saprolite for producing nickel class 1, Pak Zul?
Oh, that's a question. Okay. You can ask the question actually from the next lecture from Pak Jaki, because he will inform you more about the hydrometallurgical route to produce MHP, etc. If you see that if you use the saprolite nickel ore to produce MHP using sulfuric acid reacts with MgO, and MgO, most of MgO presence in the saprolite nickel ore. If you process the saprolite nickel ore with sulfuric acid, so the sulfuric acid consumption will be high. Yeah, this is a problem. Because of that, for hydrometallurgy, the leaching is used. Yeah, they can use sulfuric acid because the content of magnesia in the limonite is less. In the common content of magnesia in the limonite is less than 5%. In some cases, even less than 2%. It's very, very good, very suitable to process via hydrometallurgy. And on the other thing, you should also consider the cobalt content. The cobalt content is more in limonite layer compared to the saprolite layer, the cobalt. By using hydrometallurgy, you can recover nickel and cobalt at the same time. Okay?
Okay. Pak Zul, we have a lot of questions, Pak. Okay, next question is from Musoli Zaki. Hello, Pak Zul. From paper I have read, I got information that ferronickel slag composition dominated by MgO, SiO2, and FeO, yes? And if it is projected to ternary phase diagram, most of FeNi slag types lie on olivine primary phase field. Therefore, in Indonesia, slag of FeNi are mostly used as road cover or other construction material. Isn't olivine being a source of iron or magnesium metals? That's a good question. That's actually what Pak Zul do. He will explain more. Is it more profitable to use slag also as a secondary or than as construction material only? Thank you, Pak Zul.
Okay, also it's okay. We have think about that in the last 4 or 5 years to recover the valuable metal from the slag. So if you see the valuable metal in the slag is actually magnesium. Magnesium is what you call the price from magnesium is more higher compared to the iron, and also the content of iron less than 10%, less than 30%. Nobody from steel making plant interested to use the content of iron less than 30%. The common iron content for the steel making, for iron making is more than 50%, even more than 62% is common. So nobody use it. For MG, so because of that, we have made a lot of experiments in our laboratory since 2018 in order to recover magnesium. And also the idea at that time is actually to recover at the same time iron and silicon, and we can produce magnesium metals, and also we can produce ferrosilicon or ferrosilicon chromium at the same time. Is the idea. But then we realized that it's very difficult to separate or to recover the magnesium oxide if we use carbon as a reductant, because the magnesium product reacts directly with CO gas. It will convert to MgO and carbon at the end. That's okay. And for the construction material, yes, we can use it 100% for construction material. Yeah, there's a common use from slag. What is the question?
From Pak Joko Julianto, Pak Zul, is that possible to add pyrite to produce nickel pig iron or nickel matte?
Okay, thank you. To produce nickel pig iron with pyrite, no, do not do it. Please do not do it, because if we add pyrite to produce nickel pig iron, it means to add pyrite to produce nickel pig iron, it means that we add more sulfur into the product. So the product is not nickel pig iron. The product may be matte. For matte, yes. As principally yes, but we should care about the iron content in the slag. Yeah, we should take care about the iron content in slag. We should make calculation that the iron content in the slag should be not more than, we say, 20%.
Yes.
In that case, to convert the NPI or nickel, it's better to add sulfur actually. The pyrite is not new. It was tested in 1880s, something like that. It's actually the old method, and also similar with gypsum, also was added in the former time to produce nickel matte from laterite ore.
Okay, Pak Zul, thank you. Any more question, guys? You can also raise your hand here in the Zoom, and I will select you to directly ask question to Pak Zul. Okay. Any more question? There's new one. Okay, no. Okay, everybody. Any more questions?
No question. Thank you. Share. Terima kasih.
Okay, Pak Zul, it is already 12:05. Thank you very much. We appreciate for a nice lecture today, for sharing knowledge. And PK, you are raise hand or what? Or say hello? I don't know.
I was saying thank you for the nice presentation and lecture. So nothing more.
Okay.
Thank you, Professor PK.
Yeah.
You're welcome.
PK in November will visit pyrometallurgy lab, Pak Zul.
Okay.
Okay. Thank you, PK, Pak Zul, and everyone for coming. And see you again tomorrow. Tomorrow we will get lecture from Pak Zaki. Bye-bye. See you tomorrow.